Okay, I guess it's time. All righty. How was everyone's Thanksgiving? Vegan? Are you a vegan?
Family.
Vegan.
Vegan.
Vegan. What did you eat then?
Well, it was like mock turkey with stuffing and tofurkey. It actually tasted really good, maybe even better. Pretty good. Even better than real turkey.
Huh. Well, I'm glad it was enjoyable.
How about yours? What was yours?
It was nice. Had roast beef as well. I guess. I don't know. Went to bed early because I spent all night, on an airplane. And we lost Dan. Oh, okay.
Did you see that first picture of they had an octopus stuffed into a turkey?
No,
It was cool.
no, I
The
didn't,
turkey.
didn't spend too much time online the past couple of days. I haven't even sent you guys those emails out yet. I was gonna get to that during my office hour. Anyways, anybody have any questions about anything? Did you color your hair? Looks different.
Did I color it?
Yeah,
No.
looks a little different. Oh, it doesn't.
Probably
Look.
just threw out a bit.
Oh, yeah. In the past 5 days.
The turkey is
It does that.
It's possible. It's possible. Okay. Anybody have any questions on anything? I was asked what we're going to talk about today. We're going to finish up Lewis theory and talk about band, band theory and how it all connects and polar, non-polar stuff. Anybody have any other questions about anything? Oh yeah, you're good. I think I more or less stopped checking. Oh, I shouldn't say that. I've checked everyone.
now recording.
I gotta watch what I say. Anyways, okay. Everybody good on Zoom? You're hearing me fine?
Yep.
Good. All righty. So I know we talked about this a little bit on Wednesday, but I'm gonna go ahead and repeat it. Talking about polarity. And so a couple things, it deals with vectors. So if you have a linear, if they're both the same in direction and magnitude, then it's non-polar. But if you have one of the bonds that's not pulling at the same strength, then it becomes polar. So for instance, if you have carbon dioxide, this is a linear molecule. It's symmetric on both sides. This is a non-polar molecule. But say you had like a sulfur atom and not oxygen. Say you had a sulfur atom instead of an oxygen. This molecule is now polar. This molecule is polar because it's being pulled unevenly. All polar molecules all bent molecules are polar. All pyramids are polar. And with planar, if everything is even, it's non-polar. If one is different, it's polar. So like for boron trifluoride, this is a planar molecule. It's all even, it's polar. And if you look at formaldehyde, is another planar molecule. One of these atoms are different. The oxygen is different than the hydrogens. Therefore, formaldehyde is polar, but boron trifluoride with everything even is nonpolar. And then with tetrahedral, so if you have, I'll draw it in 3 dimensions. Methane, everything's the same. This is nonpolar. Then if you have chloromethane, chloromethane, this is polar because not all the atoms are same. If you put another chlorine here, so methylene chloride, this is polar, polar still, and a caution with this molecule, this is the same thing as this. So don't think of it, when you see this, think it actually means 3 dimensions. So the molecule written there is the same one, so that's still polar. And then this molecule here, this is chloroform. That's polar. And then if you have, now if we have everything on here, carbon tetrachloride, this is non-polar because everything's even. But if you have a substituted atom here, so let's have fluorotrichloromethane here. This is polar because the fluorine's different. So are you getting the gist?
It's polar, fluorine's different, but it's a halogen.
This actually is a CFC. It's a halogen. Yeah, it's a halogen, doesn't matter, but yes. Fluorine is a halogen, but it's just if one of them is different.
Okay.
Or a different atom or group. Other questions? Okay, determine if ammonia is polar. You guys like green, it's getting Christmassy. Why the heck not? So ammonia is pretty easy as far as Lewis structure. It's this, so hydrogen has 1, so 3 times 1 plus 5 times 1 is 8 electrons. 3 lines 6, lone pair 8, and then hydrogen all has a duet, and nitrogen has an octet. It's all good. So easy Lewis structure. The geometry is going to be trigonal pyramidal. And all pyramids are polar. So going up here, all pyramids are polar. So this is in fact a polar molecule. So question so far?
It's trigonal because it has a lone pair.
Because it's got 3. It's a triangle pyramid. That's a versus say a square pyramid. So this is a trigonal pyramid, and this is a square pyramid.
Why is it tetrahedral?
It's not tetra. Wait, are you talking about this? This is not. Are you talking about the electronic geometry or the molecular geometry?
The molecular.
It's not tetrahedral. So a tetrahedron. So let's see if I get a better picture. So a tetrahedron is a platonic solid, meaning that every single face for a tetrahedron, this is going to be like all equilateral triangles. So right, you have all equilateral triangles in a tetrahedron. So for the and I'll draw a tetrahedron, so it's going to be. So all of them are there, but for ammonia, the nitrogen is, I gotta make it smaller. The nitrogen is here, so then the bonds, the hydrogen in the back, hydrogen. So this bottom face, that's an equilateral triangle. But this face, whatever, like this one in the back, that one is going to be, it's going to be an isosceles triangle, but it's not an equilateral because we can't see that there. It's going to be longer in the base because an equilateral triangle, those are all the same length. So this one here, it's going to be a shorter. It's an isosceles triangle, but the we're up here, that would be an equilateral.
Mhm.
So in order for it to be a tetrahedron, they have to all be equilateral triangles, but the triangle is short.
And what makes it shorter is that it doesn't have a.
What's it-
bond.
What makes it shorter? It's just not as long. I don't know. I mean, the base. Yeah, you have the lone pair. You have the lone pair up there that sits in the equilateral vertex.
Right.
So it's just not as tall. Does that make sense?
Yeah.
So it's not a tetrahedron. It's a pyramid. I mean, tetrahedrons are pyramids, but it's like a square is a rectangle, but not all rectangles are squares. Right. So it's a pyramid, but it's not a tetrahedron because not all the faces are equilateral triangles.
Okay.
Does that make sense?
Yeah. Trying to picture.
I don't know if is there a better picture in chapter 11? I forgot. Talk about structure. Yeah, here we go. Here's a better picture.
Okay. Gotcha.
So I mean, it's not the electronic geometry is tetrahedral, but the molecular geometry is not, because in order for it to be tetrahedral, the nitrogen would have to be up here. So then these would all be.
If we added an extra hydrogen and made it ammonia, would it be?
Yes, it would be.
Okay.
Then it would be all even bonds. Yes. So if it was NH4, it was this one, then yes, that would be a tetrahedron. Other questions? Okay. So what do you think about, these are all planar molecules, by the way. These are all flat molecules. And this is trans. So this is trans 1,2-dichloroethene or ethylene. I guess ethene is more proper. Trans 1,2-dichloroethene. What do you think? Is this molecule polar or non-polar? So you have a electron draw this direction, you have electron draw in that direction. And actually hydrogens slightly go towards carbon. So you've got to draw then from both of these. So do you think these vectors all cancel out? The answer is yes, they all cancel out. This molecule is nonpolar. So I was trying to get you to think about in terms of things canceling out. And then this is cis and trans. When you have a carbon double bond, and if you have groups on the opposite side, this is known as trans. And if it's on the same side, this is known as cis. So, and I mean, chemistry has always used this lingo. It's becoming more and more ingrained in contemporary culture now because of, you probably heard of cisgender and transgender.
I haven't heard cisgender.
Yeah, cisgender is if you have the hardware of a male or female and you identify as a male or female, that's cisgendered. So same.
What's trans then?
Trans is when you have the hardware of of one gender, but you identify as another one.
Isn't that cis though?
Cis is same.
Cis is same.
Cis is same. Trans is opposite.
So I'm cisgender?
That is something you have to tell yourself.
If you identify as a man and.
If I identify with my hardware, then I'm cisgender.
Yes.
Okay. I've never heard of cisgender.
Yeah. Yeah.
I come from graduation of 2016, so.
I come from the graduation of 1997 and I've heard of it.
We had a
A
flip
flip phone. I had a flip phone. That's
No one texted me cisgender. Oh, okay.
I don't know. I mean, I mentioned that I guess I've also been trained. I'm a cisgender straight male. But that doesn't matter. It's not part of the class.
Sorry, Kim.
I guess so. Does anybody know what this is?
Irregular.
It's transparent.
regular
Transparence.
parents.
Do you get it?
Non-pol.
Transparence. Yes. No, it's a chemistry joke. That's one thing about chemistry. The humor is pretty rough. No, you should not. Is this going to be on the test?
Are there elements non-pop?
No. MA. There's not. Palladium, I think, is PA or the PD. No, not Ma. So oftentimes, so like if you have trans dichloroethene, like 1,2-dichloroethene, then this is going to be nonpolar. And if you have cis 1,2-dichloroethene, this is going to be polar. Because the vectors are going to be pointing this direction and they cancel out, and there's an overall vector in one direction. So then you have a positive end of the molecule here and a negative end of the molecule here.
And then don't the hydrogens contribute to the chlorine's vector?
It actually would, because they're going to go a little bit that way with a little bit. This is, although hydrogens are not that electronegative, and carbon's not electronegative, it's going to be like chlorine's a boulder and hydrogen's a grain of sand. But yes, it does contribute. Kind of like, does your body shift when, with the tides? And the answer is yes, it does, but not really that much.
You're talking about like,
Yeah, like the moon.
Yeah.
Like the moon's gravity. Do we feel the moon's gravity? Yes. Does it really do anything? No. So, although that's probably too harsh of an analogy, it does contribute more than that. But part of it, when you go to organic chemistry, they consider that carbon hydrogen bond to be completely covalent, and it's not. But, anyways, so if this one is nonpolar, what happens when we replace one of the atoms? Does it become polar or nonpolar? Yes, it becomes polar, right? Because where the chlorines would cancel, the fluorine has a huge vector. Fluorine is just has a huge draw. Chlorine's pretty strong, not as good as fluorine, but then because of that, you get a negative end of the molecule here and kind of a less negative. So you get a little less negative molecule here, but then a much more positive side. I'll figure we have a bigger negative. You have a buildup of negative charge there. But yeah, the whole molecule does in fact become polar. What about this one? 1,1-dichloroethene. The last molecule here. What do you think? It's not cis. It's on the same side.
So it has to be polar.
Yeah, it's going to be the same thing, right? And you get an overall, you're going to get a negative end of the molecule here, a positive end of the molecule here. This one is polar.
So that's not a cis molecule.
This is not a cis. A cis,
That's beyond specific.
it has to be on the opposite side of the,
I see.
so cis. A cis has the opposite, it's across the double bond,
Oh, I see.
opposite sides of the double bond. This is on the same side.
So
So does that molecule up there have a name
Which one?
like that on the top right? Does it have
Didn't-
a specific name?
This is 1,2 dichloroethene. Oh, I'm sorry, 1,1. I'm sorry, it's 1,1. 1,1 dichloroethene.
ethene describes the carbon.
It's the 2 carbon. You're not here yet, but so if it's a carbon single bond here, like just with hydrogens, this is ethane. Double bond, this is ethene. Triple bond, this is ethyne.
Hmm.
So the ene means double bond.
We just go down the vowels. AEF.
I guess so. Well, I guess no, because the ethyne, it's Y.
Wait, so the one in the middle, would that be like 1, 2 dichloro?
This would be 1 fluoro,
The one in the middle.
2 chloro. This has to be hyphens. 1 fluoro, 2 chloro. Actually, even before this would be trans. 1 fluoro, 2 dichloro. Ethene.
Okay, so for the bottom middle one, and I guess that's a cis one.
Well, the X, I'm just putting X to
Yeah,
mean,
if it was like chlorine or something, it'd be like the cis 1, 2 dichloroethene.
yes, exactly. Correct. But that's organic chemistry. What? Not in this class, not in 162.
Not 162 either.
No,
Oh,
no, they do that in California, not in Hawaii.
I did that in high school. That's how it's.
Okay, wow. Yeah, they teach that in California, but not in Hawaii.
Do all ionic bonds go towards the cation?
As far as the electron density,
Well, because hydrogen goes towards the carbon.
you mean like you have Na plus Cl minus? What happens?
Yeah,
Where do the,
yeah, like, yeah,
and what do you mean, where the vector is?
yeah.
Well, there's no polarity here because they're just whole ions. They're just balls of charge. Whereas for water, so this one here, the sodium has a plus 1.6 times 10 to the minus 19 Coulomb charge.
And the other one has a negative.
Yeah, and whereas like water, there's a positive part and a negative sign here. This is a partial negative, which implies it's going to be less than 1.6 times 10 to the minus 19 coulombs. And the vectors are just to show that the electrons flow towards the oxygen on the molecule. And it's just a way like, because like for carbon dioxide, so if we were to look at the electron density, so you would think that, all things being even, it would look like this. But the way the molecule actually looks like, you have more electron density around the oxygen atoms and less around the carbon. But because the draw is the same on both sides, there is no there's like a negative end in the molecule here, a negative end of the molecule here, and a positive in the center, but they cancel each other out so that carbon dioxide actually, as a molecule, has no positive or negative end. So it's slightly electron dense around the ends and slightly electron poor in the middle. But overall, it doesn't create an electronic field associated with that. Whereas water does. Have you studied electronic fields?
So I studied
Yeah. No, you haven't.
maybe like a little bit.
Yeah. Yeah, this carbon dioxide is not going to create an external electronic field. At least not a very strong one. Whereas water will. Ions, they have a huge electronic field.
Because they have a
Yeah.
positive.
Yeah, because they have a full charge. Yeah, and ions have a bigger electronic field than water, than a molecule. So. Sound good? Make sense? Yeah, that's all this stuff's not on the test. I don't mind answering questions.
Not on the test?
The talking about the charges, electronic fields, that kind of thing. This stuff is,
Those are odd questions.
yeah. Which is fine, keeps me engaged, keeps you guys engaged too, I suppose. So why do we care? Well, generally speaking, there are two types of molecules, right? You have polar and non-polar. And we have another rule called like dissolves like. Like dissolves like. So like dissolves like, meaning that polar tends to mix with polar. Polar plus polar is good. But non-polar, well, non-polar plus non-polar, I'm getting lazy. This is good, but non-polar plus polar, that doesn't happen. So polar and polar molecules, so you're gonna get a bunch of polar molecules together, they'll mix. Get a bunch of non-polar molecules together, they'll mix. But you put a non-polar molecule and a polar molecule together, they don't mix.
Like water and oil.
Yes, like water and oil. So, but you can mix other things in oil. You can mix gasoline and oil together, right? Gasoline is non-polar. And for water though, you can mix things like vinegar. Vinegar is polar. You can mix that with water, no sweat. But you throw olive oil and vinegar together, what happens? They separate, right? So, and you can get them to mix together a little bit. So you can take olive oil and vinegar and you can mix it like you have Italian dressing, you shake it up and you can make kind of a temporary emulsion of sorts. But then if you let it sit for a little bit, what happens? Separates. So a lot of people think that oil hates water. It's actually the other way around. Water hates oil. So here is my artist's impression of oil. Oil is a long non-polar molecule. And oils, and even various length, gasoline is kind of a branched molecule. So they can all mix together fine. They're going to have similar, they're just big non-polar molecules. Water is a pretty tiny molecule. And water, though, because it has a positive and negative end, what happens is there's a bonding with water. Water bonds with itself. And because there's a positive end of the molecule and a negative end of the molecule. Now, let's say that you are an electron cloud and you see another oil molecule. So your choices are another oil molecule here or the positive end of a water molecule. Which one are you more attracted to? The really diffuse electron cloud. So if you're this molecule here, which one are you more attracted to? The diffuse electron cloud of this molecule or the positively charged end of the water molecule? it's going to be the water. Oil loves water. So because water has a charge, and if an electron sees a charge, so here's your nonpolar molecule, big long nonpolar molecule, and here's the water molecule, and it says, oh, you got a positive end here. I'm really attracted to you. I want to get close to you, water. And so the molecule kind of moves toward water. So what the water does is it goes, get away. Yes. Yeah. And like, ooh, another water. And then they have a bond. So actually what happens when you mix oil and water, the water literally pushes the molecules out of the way. They're like, get out of here. I want to get towards my my fellow polar molecule, because there's a bonding there. And I mean, there's bonding also with the nonpolar molecules. We'll talk about that next semester. But then because of gravity though, we're in a gravitational field. So then, and water is more dense. So the water goes on the bottom, and the oils tend to be, the mixtures tend to be less dense than water, and then they float on the top. So it's actually the way around. Like the oil loves water. It wants to be with water. Like water, where have you been all my life? Water's like, get away from me. Bad oil. You're ruining up my bonding network. So
Have they done this experiment in space?
I'm not sure. You'll still have you'll have droplets at least forming. It's going to happen on a small scale, but you'd still have to be pressurized. It's hard to get a liquid phase. So liquid phase is a very weird thing, because you have to have sufficient pressure, and it's kind of weird that you would have pressure but no gravity, right? So this would only happen in a space station. So. But well, there's a couple things. There's some molecules actually mix with both. So alcohol, for instance, like ethyl alcohol, because we have ethyl alcohol in gasoline. So actually, ethanol is a weird substance because it dissolves both in polar and nonpolar. But most molecules go for either polar or nonpolar. And also with that, vitamins. So there's certain vitamins you need to take every day. So vitamin C and vitamin Bs, those are water soluble. And it's really, really hard to overdose on those vitamins. Extremely difficult, because anything you don't use, you basically pee out. So you renally, I should say, sorry, I'm going to record. You renally excrete them. Here we go. So some vitamins though you store, vitamin A, D, E, and K. And some of those can be dangerous. Vitamin E is not bad. Vitamin D, also not bad. Vitamin A, it's really hard to overdose on vitamin A. Beta carotene, you can have all you want. You actually can overdose on vitamin A, but the only time you really do that is if you eat polar bear livers. So apparently polar bear liver is a huge source of vitamin A. So with the exception of eating polar bears, you're not going to overdose on vitamin A. Vitamin K though, vitamin K can be an issue because vitamin K. Does anybody know what vitamin K does? Causes your blood to what?
Constipation?
No,
No.
coagulation. Calcium can cause constipation. Too much calcium can do that.
That explains it.
So, and magnesium does the opposite. Funny enough, but anyways,
What about this guy?
you talking about bismuth subsilicate? Bismuth isn't going to do that much. The elements. Bismuth subsilicate, it tends to do both. It coats your, well, it stops either one because it coats your digestive system. Except it can promote stomach bleeding.
Oh.
So it depends on what you're treating. So, but even more so, there's a magic molecule called soap. Has anyone ever thought about how soap works? I mean, right? Like if you've ever you were just probably just cooking Thanksgiving dinner and your hands were all greasy. So what do? You can like you run your hand under hot water, and you still you got that feel, and then maybe you start rubbing your hand with a towel and stuff, but then you're like, oh, I know, I'll use soap, and you soap it up, and then you're okay. You're not mirroring me? Okay.
What? I want to be like perfect.
I'm trying to mime it also for the online folks.
I'll just do it.
Yeah, I know. But then you didn't follow me. So I was like, haha. Anyways, so but a couple things to notice, like when you have a greasy hands, you don't just put soap on your hands and then you just sit there and then the stuff goes away, right? You actually have to go underwater and then rub your hands together. So rubbing your hands is important. It does something magical, and there's something magical about soap. So the way soap works is that you have a polar head and you have a non-polar head, so a non-polar end. So you have the fatty acid here, well, a hydrocarbon here, and for soap, it's usually about 25 carbons in length. And then you have a polar end of the molecule. So, and in soap's case, most soap, it's negatively charged. It's usually anionic. So you have an anionic surfactant. So surfactant is something that breaks down the surface tension of water. And so you have a negative end, and usually you have a counter ion. It's usually sodium or potassium. It's Castile soap, but usually cheap stuff is sodium. So anyways, you have a negative end molecule, and what happens is you can form what's called a micelle. And that's when you rub your hands together. So when you clean your dishes, you put soap on them and then you rub them with a sponge, right? And then that creates bubbles or whatever, and that's what the magic that gets all the grease off the pan. Same thing, your hands. Your hands are greasy, you put soap on them and you rub them. What the rubbing does is it creates these micelles. You're creating these micelles, and the micelle is it's an oil droplet surrounded by the polar ends. The non-polar ends go towards the oil droplet. The negative ends go to the outside. Now this whole micelle can be water soluble. And the coronavirus more like, not quite, but it's really close together. And it's a sphere.
But you're saying that the non-polar end sticks into the oil
Yes,
and has the polar head.
on the outside.
Yes.
But then they eventually stick together again to wash it away. Is that how
Well, this whole thing, the whole sphere, it's,
the whole sphere that they collect?
yeah, and then they wash away. Yeah. Does this look like this structure here, this micelle, does it look like anything to anybody? Anyone think of what it looks like
Those
besides coronavirus?
Truffle tree.
A what?
Truffle tree.
A truffle? I've never heard of that before. Does anybody know what a cell membrane is made of?
hydrocarbons.
They're made of like
Phospholipid bilayer, yes. A cell membrane is a phospholipid bilayer. So you have a phosphate group, lipid is a fat group, bi means two, a bilayer means two layers. So a phospholipid bilayer is a anionic surfactant that happens to have a phosphorus group on it, and you have two of them, and then it forms a bilayer. So that's what so when you have a cell membrane is just like a micelle, but it's just two molecules thick. So isn't that kind of crazy that you have, like, how we separate cells? Also, the organelles inside your cells also have phospholipid bilayers. So things like, although we don't have them, but chloroplasts or mitochondria, like all these things, they all have phospholipid bilayers. So you have in a cell, you have other things in the cell, and the skin of them is just two molecules thick. And for most animals, the carbon chain is around 25 carbon atoms. So you're looking at, 50-ish atoms kind of going through for a cell membrane.
You see, Fight Club?
Yeah, so how they made the soap. Yep.
Yeah.
The book is funnier. You get a chance to read the book. It's hilarious. Better than the movie. But yeah, so that's a so what. Like dissolves like. And the applications for that are, of course, certain things things are soluble in like things. So like how we get things to dissolve. But an application of that is vitamins. So certain vitamins are lipophilic. Lipophilic means fat loving. So they dissolve into your fatty tissues, your body stores them. Vitamin A, D, E, and K, your body stores. Other ones are water soluble. Vitamin B's and vitamin C are water soluble. So your body, you need to ingest those every day. So also, I don't mention drugs. Certain drugs are fat soluble. And so like cannabinoids and PCP, for instance, are very lipophilic. Your body stores those. And other drugs like alcohol. So other drugs go through your system pretty quickly. Although you can't find them in your hair. Things like cocaine tend not to be stored in your body, but you can find them in your hair. So that's why they do hair tests and the blood test. So actually, cannabinoids, they stay in your system for a very long time.
Like a month.
Yeah. So they take just because they stick to your fatty tissues. But okay. And that's the magic of soap. Anybody have any questions so far?
So does, when you use soap, does it rip apart the biolayer?
Well, it's a monolayer. It's not a, are you talking about for
Like viruses?
viruses? Yeah. Yes, it can.
Okay. But it doesn't affect our skin. Like, it doesn't affect the cells.
Our skin, if you look at skin, you have we have a layer of oil on the top of our skin. It's called sebum or sebum. And below that is slightly acidic, and it's an acid layer, a pH of around 5.5. Then you have around 20 or so your cells of your epidermis that are keratinized skin cells. So it's cells that are just completely made of the protein keratin. Keratin is your fingernails, skin, and hair are all made of the same stuff. It's keratin. It's kind of like, it looks kind of like layered like steel cables. If you like, well, it's not necessarily under a microscope, but it's a protein that's made almost entirely of what's called an alpha helix. So it's a swirly protein, and there's just long strands of it. And although our skin has kind of like scales on it, but it's just all that single protein, usually around 20-ish cells thick. So soap, though, you can strip the sebum and the acid mantle off, but it's not going to strip the keratinized cells. So although over time, losing all the oil can cause issues. Specifically, a condition called contact dermatitis, although you can get dermatitis other ways, but contact dermatitis is like, that's if you wash your hands constantly. And some people are probably getting it from the pandemic, to be honest with you.
I think my brother had that, he was using shampoo for washing his hands.
Shampoo is actually weaker soap. So I would be surprised unless he washed his hands longer, or maybe he's allergic to something in the shampoo.
Where it like makes a rash, right?
Yeah. And that would be dermatitis. That's dermatitis. The dermatitis just means inflamed skin, but it's probably from one of the components that's in the shampoo. Because shampoo is just kind of like poorly performing soap. So yeah, but my cells, from your earlier question, it's not going to burst. I guess, well, it can. It depends on well, viruses, they have a protein coat, and you can, with ions, you can also burst viruses. So, but yeah, washing your hands does burst viruses. So you can kill viruses that way. Bacteria, Well, this is where science and legal issues differ. All soap is antibacterial. Okay, so does soap kill bacteria? Yes, it does. Soap has been killing bacteria since the ancient Egyptians invented it back 4,000 years ago. So, or actually, no, I guess it'll be 6,000, it's 4,000 BC. So 6,000 years ago.
They knew about bacteria?
No,
Oh.
no, they just knew that they found soap and they found anecdotally, yeah, a lot of like the religious laws and whatnot, they deal with, I mean, just practices that are just hygienic. Ancient Egyptians also figured out how to filter water. They use sand filters to filter water. And it's actually the bacteria that was in the sand is what ate all the like the bad things. So what?
Wait, so they use sand to filter and it just made it worse?
No, it makes it better.
Oh, I thought you said the sand bacteria.
The sand bacteria, well, it's impurities. So
Oh,
and
okay.
and they can also, and it's relatively benign. Not all bacteria is dangerous. So it's only pathogenic, it's only disease causing bacteria is dangerous. Like we're covered in bacteria right now. So that's our microbiome. No, they're in certain, even bacteria from other animals. Like I have cats, like, cat bacteria tends not to bother humans. Same thing with most animals, at least most domesticated animals. But then you get things like pig, well, I guess it's like boars and mongooses, right? You can get like leptospirosis and cryptosporidia from them. So that's pathogenic. But we humans, we've evolved to handle the bacteria from our domesticated animals. I'm not advocating you go start rubbing manure on your face, but I mean, it's not going to harm you the same way, like, I don't know, non-domestic, like if you went and did that with a mongoose, and that might be a little different. You might get a different response. Andre's doing this.
I work at a ranch, so give me any ideas.
Hey, that's something different. Yeah, that's Darwinism right there. Other questions? This is fun. I'm enjoying these talks. I hope not the Zoom's going like, what the heck's going on? All right. All right, so we're going to move on and talk about something different. Again, let me preface this. This is all wrong. This is not true.
Why am I coming to school?
It's still useful. And again, this is trying to explain away, and all these phenomena are true, but they're trying to explain it away. Valence bond theory. And if you look at this graph, this describes a bonding scheme. So you have hydrogen atoms. So here's hydrogen in very long distance from each other, but as two hydrogen atoms, as they approach each other. So if you look at hydrogens as they approach each other, and you look at the potential energy. So that if this is the y-axis is the potential energy, x-axis is the distance. So as you have things approach each other, they start to bond, and then the energy goes to a minimum here, and there's like an idealized thing. And then, of course, if they start getting too close, then the positive centers of the nuclei start to get close to each other, and then they repel. So then the potential energy goes up. So there's actually the potential energy, and they become repulsive as they get closer. And you probably know this from your friends too. If you really like someone, you like being close to that person. But you can also be too close to someone, right? So I mean, it's kind of like idealized is kind of like, arm's length. Like, here's my really good friend right here. Of course, the person's like in your face, like, dude, I like you, but you're my face. You don't necessarily like that. And that's when you get to this stage here. Like you're in my face. I find this repulsive. So, well, most people do. Well, within a certain distance. How many angstroms you get close? So, all right. So, and actually the shape of this graph, if you want history, this is also known as a Leonard-Jones 612 potential. So because it's the polynomial has the x to the 12th and x to the 6th in it. But also Leonard, he was it was scandalous at the time. He was so in love with his wife that he took her last name. Well, he hyphenated himself. After Leonard married Jones, he himself became Leonard Jones.
Did she do the same?
I don't know. I think so. So, and this puts an issue though. So like hydrogen sulfide. So when you have a hydrogen sulfide, before we said this is a bent molecule with VSEPR, it's going to be a bent molecule and the bond angle is going to be slightly less. So then this bonding, let me draw the molecule better. Here's hydrogen sulfide. And then we would think this angle would be slightly less than, the angle is going to be less than, I shouldn't put the, here we go, it's going to be this way, 109.5, right? So the big region of negative charge is going to push down, and with the VSEPR theory, you're going to have a bond angle slightly less than 109.5. If you look at the atomic orbitals of sulfur, so sulfur is going to be, so it's going to be neon 3s2 3p4. So there, and so then hydrogen, the idea is that the electron orbitals overlap with the valence band theory, and the p orbitals, if you remember, they're all perpendicular. So you're looking at the p orbitals only, you would expect the bond angle here to be 90 degrees, but it's not 90 degrees. It's closer to it's slightly less than a tetrahedron. So same thing with methane. You would think then the bond angles actually would be, I mean, not a Fisher diagram in 3D, but you would think that the bonds would all be perpendicular, but they're actually a tetrahedron. And how do we get around that? And although this, like I said, this theory is kind of fundamentally wrong, much of organic chemistry is based on it. So you still need to know it. And the truth of the matter is this theory works most of the time. It's just not the real reason why things bond. And we'll get into that probably on Wednesday. I don't know how many questions you ask. But the idea is that the s and the p orbitals, they come together and they hybridize. So meaning you have an s orbital and 3 p orbitals, and they hybridize to form sp3 orbitals. And there's 4 of them. And they all together, they fit to a perfect tetrahedron. And so now this explains the geometry better of methane, where you have the sp3 hybridized orbitals, and now hydrogen then can overlap between them. And I said that this is not the proper theory. What happens is that the hydrogen and the carbons and the electrons between them, and then the electron cloud between them, the 2 atomic centers, they form, and with the combination of the electronic and magnetic fields of the electrons, they form new orbitals, and then the electrons populate in those energy levels. So and to describe that, you'd have to understand we do a lot more math and look more all that stuff. And I recommend that you learn those skills, but that is above and beyond this class. The earliest you would really see that is your junior year as an undergrad, and you'd probably see it more in depth in your first year of graduate school. So
So every element, every molecule would have its own unique orbital.
yes,
Okay.
that's why we can do spectroscopy on them.
Not even like relative to the orbitals we know for a single atom.
They're not gonna, yeah, they're not gonna be the same as the atomic orbitals. They're gonna be new molecular orbitals. So that's why we can use like the James Webb Space Telescope that's still here on Earth to look at molecules out in space. But okay, so I mean, that's so what I mentioned there, that's the truth. That's where eventually we're building up to. But this shortcut using the model and using the word, so the model, this is a model, it's a representation, and it works pretty well. So, but the hybridized orbitals, and you will use that model quite a bit in organic chemistry. So what about, that's for single bonds. What about double bonds? So instead of sp3, you can have what's sp2. So only two of the p orbitals will hybridize, and you'll get 3 sp2 orbitals and 1 just plain old atomic p orbital. And then you would have as this, and then this is going to be for the planar geometry. So the up here, this is going to be tetrahedral. So the tetrahedral electronic geometry is going to be sp3, and planar geometry is all going to be sp2. And this also talks about the different types of bonds. So if you look here for formaldehyde, so formaldehyde, let me draw the Lewis structure. That's the Lewis structure for formaldehyde. And so it's a planar molecule. And the idea here is that you have, so if this is right here, you have the plane. So you have the plane that they're in, and then you have these open p orbitals. Well, you have another, well, for oxygen, you can have bonding here along those, the orbitals for oxygen. And now you have these open p orbitals, and between them, you can have overlap above and below the bond here. And we give this a certain type of bond name. We call this a pi bond. So you have sigma bonds. So you can see here, this is the Greek letter sigma. So this is a sigma, and this is, let's lowercase sigma, and this is going to be lowercase pi. Fortunately, we haven't got that high with our variance yet, right? So, and a sigma bond, I'll see if I can, all right, so you can see me. So a sigma bond is a bond between the internuclear axis. So meaning if I have an atom here and an atom here, so a sigma bond is along the internuclear axis, and the internuclear axis is actually like it's my arm, basically, right? So this is a sigma bond. But a live transfusion, okay. So a pi bond, though, so if sigma bond is along the internuclear axis, a pi bond is above and below, so it's like here. So, and that can also be here in this dimension as well. So here, pi bond here, you have a pi bond here. So if you've noticed, all single bonds, every single bond is a sigma bond. So in a double bond is a sigma bond and a pi bond. A triple bond is sigma bond, pi bond here, and pi bond here. So having the axis rotated by 90 degrees. So here we go. So we have a sigma bond and a pi bond. And for this molecule here, for formaldehyde, so you can see here, sigma bond parallel to the internuclear axis, pi bond above and below internuclear axis. So then for formaldehyde, so for here, a sigma bond, there's a sigma bond here, sigma bond here, sigma bond here, and then a pi bond. You have a pi bond. So formaldehyde has 3 sigma and 1 pi bond, because the single bonds are sigma bonds and a double bond is a sigma bond and a pi bond. So, and also with this, you have with single bonds, you have free rotation, right? So free rotation is easy. So if I have my bond, I have a single bond, it's real easy for this to rotate. So if I have a molecule, it's all single bonded, a single bond, it's real easy to move this bond, flap around. It can twist, it can turn. If it's like this, if it's a long group, this group can flop around, no problem.
So it can connect to other molecules?
It can, although it tends, it depends on the temperature. So if you say my head is a group and this is a group, actually it tends to kind of go in this direction. And this is called the gauche. But it's still at a higher temperature, it's going to be flopping around, but it just prefers to be further because the steric, and for the negative clouds like to be as far away from each other as possible. But at high temperature, high energy, it's flopping around. So, but now if you put a pi bond, so if I have a pi bond, I have 2 groups. So here's 2 groups, and say I have a pi bond. So this here is cis. I'm not very flexible. And this here is trans. So right, cis and trans. Actually, you can see trans is actually lower energy. Trans is preferential to cis. Cis because these things will, the big electronic negative groups are here. Trans tends to be farther away. So, but because there's a double bond here, to go from cis to trans, it takes a lot of, you have to break the double bond, right? Because the p orbitals, so when you have, they're above and below, and if you rotate it by 90 degrees, you're going to break that overlap. So you have to break a pi bond in order to do that. So it turns out cis and trans is actually really hard to switch in between them. Although it's still done. It's still done quite a bit. Our eyes work in part because we have a molecule here, the cis retinal. When you have and this was in our rods. So, well, I guess the rods and our cones. When light hits this, when a photon with enough energy hits this, it'll convert cis retinal to trans retinal. So, and it takes that extra energy, and that's how our eyes can pick up the photons. So, and that's how our eyes work. Also, I haven't mentioned this quite yet. Does anybody know what's something bad? Like if you think of bad fats, like what's in margarine, what do we have in margarine that everyone thinks is so evil? Fat, but there's a word in front of the fat. Trans fats. All biological fats. So we wonder some things about like life on Earth. So all life on Earth has cis fats, meaning, and have you heard of saturated fats and unsaturated fats? Do you know what saturated versus unsaturated means? Part of it, yeah. Do you know, so that's a good point. Saturated fats have more hydrogen, but what I was looking, then you are correct, but what I was looking for is that unsaturated fats have more double and triple bonds in them. Yeah.
Because the carbon takes away from the.
Yeah. Yeah, and so a double bond means there's gonna be cis trans isomerization, and all natural fats have cis bonds in them. They're all cis. So, but you can when you hydrogenate oils, if you wonder how you hydrogenate oils, you put hydrogen, you put acid in them. So if you want to make margarine, you take olive oil and you put some in like vinegar in it, and you heat it up, and you'll get margarine. And you stir it around, you'll get hydrogenated oils, and when you have a triple bond, you're gonna add hydrogen to it. You're gonna get rid of one of the. Get rid of the carbon. You get rid of one of these, and now you're gonna have cis and trans with that. But you're gonna have about a 50-50 mixture, but it's gonna slightly be more trans than cis. So, and our bodies are just used to cis fats. So that means that it's just something we're not used to. So that's why trans fats can be bad. It's just your body like, what is this stuff? It's kind of like cis fats, but it's not cis fats. And you have to switch it back to cis. So to make it usable. But it puts a little stress on you, but it's not too bad. I mean, trans fats are not the end of the world. But it's just something our bodies haven't really seen in appreciable amounts before the 1850s when they started doing margarine.
And they, like a law or something, that companies can't have it in their products.
I haven't heard that.
Because like whenever you look at a product, like the nutrition facts, trans fats, usually 0.
Well, they're just trying to say they're healthy.
They probably are trans fats.
It's hard to say. Probably not to an appreciable amount. I mean, there probably are a little bit, but I mean, that's like saying, are there any atoms of plutonium in this room? Like there probably are, but not a whole lot. So, all right. So explains why cis trans. And let's go back to VSEPR. We talk about electronic geometries, and you remember when I mentioned when I was doing the chart, I said, oh, when you have the different geometries, you have the different hybridizations. Linear has SP, planar has SP. Oh, I didn't talk about triple bonds yet. Oh, when you have triple bonds, did I talk about, sorry, is it? Oh, I didn't talk about triple, okay. Triple bonds, similar to sp2, you're going to have just S and P, and the S and P orbitals, they look like this. And then you have two of them and they form the linear shape. And in my notes, I can see I can talk about dinitrogen. We'll get there. So two electron groups, linear geometry, electronic geometry, SP hybridization. 3 for planar, you have sp2 hybridization. 4 tetrahedral, sp3 hybridization. And then when I mentioned above, so group period 3 and above can go into expanded octets, and this is the reason why, because you can have the bipyramidal sp3d hybridized orbitals, and then the octahedral sp3d2 orbitals. Oh wow, I'm looking at the transcript. It really says octahedral bad. Oh, usual bad. Huh, octahedral. Someone wanted to see the transcript of this. All right, so let's see. Oh, wait. And let's look at the hybridization and bond scheme for ethylene. So ethylene here. And let me draw it this way. This is an interesting molecule, by the way. I guess most molecules are interesting. So ethene or ethylene. Well, you ever smelled like ripening fruit and notice the smell that it gives off? Like especially bananas. I think about bananas a lot. Like that if you smell that, and you can smell it with all fruit too, that's ethylene that you're smelling, or ethene. And this molecule is also it's causes fruit to ripen. So you ever heard some of the things like a one bad apple spoils a whole bunch kind of thing? If you trap in ethylene, it causes ripening to happen faster. So that's something called autocatalytic. If fruit is ripening, it releases more ethylene, and ethylene makes it ripen faster, so it can be a runaway effect. And that's also if you want to like get things ripen faster, you put it into like paper bags or something like that, because you trap in more ethylene and then it causes to ripen faster. So yeah, it's common for avocados. Usually you want fruit to ripen more slowly. But anyways, with this, it's so the carbon's going to have three things in it. So this carbon here has three things. So three things means trigonal planar, which means sp2 hybridized orbitals. And then you have sigma bonds. I'm going to do this with this. You have a sigma bond here, a sigma bond here, and a sigma bond here. Same thing in the other one. You have a sigma bond there, sigma bond there. But you also have the open p orbitals here, and then these p orbitals not along the internuclear axis can have a pi bond. So this molecule has 5 sigma bonds and 1 pi bond. And this is a prettier picture. So also does it tell you the single is a sigma bond, double is a sigma and a pi, a triple is 1 sigma and 2 pi. So let's see, can you follow? Can you see what the hybridization is in sulfur and SF6? So SF6 is going to be octahedral geometry because there's 6 things. Octahedral geometry is going to be sp3d2. So this is sp3d2. So do you see how to do that? Okay, and dinitrogen is really, I'm kind of emphasizing the di has how many pi bonds. So nitrogen, here's the Lewis structure for nitrogen. So it's just got 2 things, right? So this nitrogen here sees 2 things. It sees a lone pair and it sees a nitrogen. So 2 things. 2 things means linear geometry, and that means sp. So you have the sp orbital, and you have the other nitrogen has an sp orbital. So you got the overlap here, and you have the lone pair sitting here. And then you have 2 p orbitals. You have p orbitals here, and then see if maybe I'll use orange. You can see the orange there. So you're going to have overlap there, and you can have overlap here. So you're going to have, if you look at the bonding, you're going to have a sigma bond here, a pi bond here, and a pi bond here. So 2 pi and 1 sigma. So how many in dinitrogen? It's going to be 2 pi bonds because the triple bond, right? So triple bond. So that's that.
So, for the most part, this is right. This theory.
Most part. But if you look at this molecule, the dinitrogen, you'd expect the electron density to look like a clover leaf, right? Like a 4-leaf clover. But it really turns out to be a cylinder.
Mhm.
So it's more like a cylinder. It's much more symmetric than like 2 4-leaf clovers. It tends to be more symmetric. It's pretty close. It's pretty good. It's a good model, but it's not exactly right. So, and I'm 1 minute away from my shut up alarm. Oh, and there's a shut up alarm. All right, shut up alarm. It's time to end class. Anybody have any questions?
Typically last day of school is just the Friday before, like the last Friday before Thanksgiving.
Oh, wait, the last day of class is the Thursday, next week, Thursday. Yes,
Really?
Really?
because the Friday is a study day. The 17th, wait, that's,
Today's the 28th or 9th.
You guys asking about-
here, better.
Last day.
Oh, yeah, like, yeah.
17th is the last day of the test.
Yeah, that's the last day, the 9th, December 9th is the last day of the term. Like, well, last day, like the last day that we'll meet is December the 8th.
Oh, okay.
Okay, so.
December 9th, though, is the last day of the semester.
Gotcha.
And finals week is the 13th to the 17th. You can see that I'm flying out. It tells you.
Wow.
Like, see you suckers. All right, see you later. Chicago. See my family, Christmas. Oh, you're welcome. Yeah, once I'm required to be here until the end of whatever, until the end of finals week, and I'm actually my duty quasi ends at 4:30 on Friday afternoon.
Oh, okay. When do you have to be back as a teacher?
January 3rd.